Um, so we're going to talk briefly about an amazing technique. And all right, hold on. I need. I'm going to talk briefly about an amazing technique that is used all the time in machine learning. And this is called wisdom of the crowd. All right, so here's the basic idea. The idea, actually, according to the story, goes back to Galton. Galton was a cousin of Charles Darwin, if I remember correctly, famous scientist, famous statistician. And one day, as the story goes, he was at the state fair, or the UK fair, and he saw that there was an auction. They were auctioning out an ox. And the auction was that everyone had to make a guess of how much that ox weighed. And you had to pay a penny to enter to the auction. So you paid the penny, you made a guess, you wrote it down in a piece of paper, if that sounds familiar, and you hand it out. And whoever got closest to the actual weight of the ox actually took the ox home. Now, that was in the late 1890s, so I guess that was the thing back then. I don't think that would be very popular right now. I mean, you could take the ox home, but I don't know what you do with it, right? So maybe put it in the garage. As the story goes, no one got the exact weight, but there were a few close guesses. And then the question that Galton asked is, what happens if I aggregate all the guesses that people made? So he asked the auctioneer if he wouldn't mind sharing all the guesses, all the pieces of papers with him. And the auctioneer said, you know, this auction is over, so here you go, here are all the pieces. So he went home and he computed the arithmetic mean, or the sample mean, that we described the other day in class. And to his surprise, the guess of the average of the population was the exact weight of the ox, right? So this is what's been called the wisdom of the crowd. This is the idea behind the mean, that if you can have multiple guesses of something, whatever it is better to trust the mean of those guesses than actually just trust one of them, right? Or any one selection of them that is not similar to the mean. And I'll get to that in a second. Now, this actually goes way back before Galton. Plato, in his book, Republic, he actually talked about this. So Plato talked about democracy, and that was back in 38 BCE. So it's a few years before, right? Almost 2,000 years before Galton, or 1900. And Plato's argument was that we have to give the vote to the people. We have to give democracy in a way that people can have representatives that are chosen by the people. And his argument went like this: how can I give the vote to the people if the people are uneducated and don't know what, or don't have the enough knowledge to make an informed decision? And his argument, or his counter argument then, was that if you aggregate the votes across the population, then the wisdom of the crowd will actually pick up the correct individuals, right? That's the or one of the tenets by which we still abide today, right? We're still using this in many representative democracies. So this is a technique that has been in discussion for thousands of years now. And the question is whether it works or it does not work, right? And the answer is it depends. It depends on what type of mean you use, and we'll get to that in a second, and it depends on the problem. So if you asked back in 1895, whenever that was, what the weight of an ox was, people were very familiar with oxes, so they could probably make a good estimated, a good intelligent guess. But today, I would assume that if they ask us, we would be completely clueless about what an ox weighs, right? And the same goes for estimating the number of taxi cabs that there are in New York City. So I asked you this the other day, and the results are in, and we tabulated them, and they are very good estimates. They go down, okay, let's see, the minimum, the person that estimated the smallest number of taxi cabs is 0. I think it's larger than 0. The person that estimated the maximum number of taxis in New York City is 10 million. I don't think that's right either. So that's a problem, isn't it? By the way, the population of New York City is 8.5 million, so 10 million cabs, that would be good. Taxi to person ratio. So here's the problem, right? That you have to know something about New York City. You have to have some information. If you don't, this is how you should, because these problems will occur in your career, especially if you work in machine learning, over and over again, or in programming in general, right? In engineering in general, it will occur over and over again. You'll have problems. Maybe we can play another one. Maybe I'll post something in Carmen later on, and we can play with that. But there are problems like this that you will see over and over again. And the question is, how do I estimate that, right? How do I make a guess? Well, you should start with how many people live in New York City, right? Now, you may not know that, right? You may be from another country. You may be from another state, has never bothered to check how many people live in New York City, right? But let's think about this. Do you think that there are more or less than 1,000 people in New York City? More? Okay. How about 10,000? How about 100,000? Right? How about 1 million? Certainly more than 1 million, right? How about 10 million? Ooh, right? That's where we go, we're not sure, but certainly not 100 million, right? So it's somewhere between 10 million and 1 million, right? So just pick a number. It doesn't matter. It's within an order of magnitude, right? So as long as you get an order of magnitude, you're not going to be completely off, right? So pick the middle point. Let's say if you have no idea, I probably pick 10 million, but if you have no idea, say 5 million, right? What have you? I would pick personally 10 million as a good rounding number if I had no idea of the exact 8.5, right? Okay, so let's say 10 million. I'm overestimating, but it doesn't matter. Then how many people will use a taxi cab at a particular point in a city like New York City? I mean, is it, let's think, is it 100% of the population? Of course not, right? Is it 50% of the population, half the population? No way. Is it 10% of the population? That's absurd. Or 10% of the population are not even on the street, let alone on in a taxi, right? Is it 1% of the population? 0.1%, right? So you can say, well, maybe, I don't know, maybe it's 1%, right? You can go with that. And of those, how many are actually in the taxi right now rather than waiting or getting off the taxi and changing, right? Maybe half of that. So maybe we're down to 0.05%, right? So then you can start going down, right? And say if you started with 10 million or 5 million, right? You say, okay, what would be a 0.5% of 5 million or 10 million, right? Where is it? Anyone? Oh, come on. What's that? 5, 10,000? Is that what you're saying? 5,000? Okay, anyone else? Okay, so let's say between 10,000 and 100,000. How about that? Okay, we'll go between that, right? Between 10,000 and 100,000, right? That is if you had 1% of the population in a taxi, right? That's absurd, right? Obviously, you're not going to have that much, right? So maybe, as we said, maybe it's going to be something in between those two numbers. So maybe 30,000, 40,000, 50,000, thereabouts. All right, the actual number is, let me see, 13,587. All right, we got within an order of magnitude. It's not bad, right? That's not bad. All right. Now, what is the wisdom of this crowd on this particular problem? So your average, your sample mean, is 600. Okay, let's see. You really think there are so many taxis in New York City? So the actual number, that's not going to work. That's why I have my own. Huh? All right. The actual number is 13,587, right? Yep. Okay. Your mean is 629,674. It's not even within an order of magnitude. It's terrible. Okay. As I said, the mean is 0, the maximum is 10 million. So this is what's happening, right? That there are several people that estimated 10 million. I see a 30 million. I'm sorry, 3 million, a 5 million. It is just, that's moving us away. Right? What statistic other than the mean could we use to avoid these outliers? The median. Very good. So what happens if I compute the median? The median is 50,000. Not bad, right? At least it's within an order of magnitude. That's not bad. That was, by the way, the estimate that we had with this bold, crazy search that we were doing. So that's pretty good. All right. We had 3 winners. All of them estimated 14,000. It's a very good estimate. Wow, I'm impressed. Okay. The names are Sengyang, Lin Ryu, and Anonymous. There's always an anonymous, right? This famous guy. I don't know. Never met him, but famous guy. All right. So good job, guys. All right, so how are we going to solve this problem? We have to improve this somehow, right? Because the wisdom of the crowd is used all the time. When we get to deep learning, for example, I'll talk about this. One of the things that people do in competitions, not really when they design their own system in-house, but when they participate in competitions, what they'll do, they'll have a big network, one of these huge networks that are typical now, and they'll either train it using different different epochs or different iterations, different training samples, or they'll use different outputs of the network and then compute either the winner takes all or the average or something of that nature to actually get a better estimate of the outcome, right? So it's actually very typical. But obviously, as you can see, not so good. So could I have asked you another question, other than the obvious, how many taxis do you estimate there are in New York City? Could have asked you a second question that would have allowed me to get a better estimate of that. Can you speak up? I can hear you. No, but if I just ask you as an individual. Yeah. Okay, that could be, but that's probably, you're right, that could help, right? That could help people focus on how many people in New York City are actually in a taxi. So there cannot be that many more taxis than people are using, because otherwise it's losing business. So that might help. That's a good idea. What else? I'm thinking about a completely unrelated question. Well, very related, but not to the taxi. Again, that's a related question that might help, right? But that's not what I'm looking for. You're right. How what?
How often do you take the test?
What do you mean, how often do you take the test? Oh, the taxi? Same thing, yeah. Don't think about New York City. Think about this problem. How are we going to address the problem of these outliers? One way is the median, obviously, but there are other ways, yes. How? If you can explain the answer. Okay, and what do I do with that? You're going in the right direction. What do I do with that? But that's just changing the question again, right? That's restating the same question in a different way, which might help, as I said. But that's not what I need. I need to know something about each individual answer, and that I can ask the person that provides the answer. Yes. No. That's another statistic, right? So you're right. So one way to do this is we can compute the mean is just one statistic. We could use the bias mean, the unbiased mean. We could use a median. We could use the mode, right? I actually think I computed the mode, or maybe not. See. I thought I had computed the mode. No, I don't have it. But anyways, you could compute a variety of statistics, right? But I'm looking for a new statistic which is similar to the mean, but I need to ask you another question in order to use that. Yeah. Oh, but that's already in the mean, right? Because the mean is the sum of all the observations that I have divided by the number of observations, right? So that the sample mean already has that. How are you going to improve that equation? So I want to ask another question to improve that equation to get a better estimate. How what? Very good. How about if I ask, how confident are you, right, about your answer? If I ask you about a confidence number, say between 0 and 1, then I can assign this as another variable that, or I can assign that number to a variable. Usually we'll call this the weight or the confidence. And now I can have wi xi such that I weight the confidence of each estimate. That tends to work better, but surprisingly, it doesn't work much better. Surprisingly, people are terrible at estimating their confidence. And this is really bad. I mean, think about this. The way we vote in elections, obviously, in research, the way we evaluate papers, research papers, so what we do is people, when they complete their research, they write a paper, and they submit a paper to a journal or a conference, and that gets reviewed by your peers. And your peers, actually, in the reviews, you provide your evaluation, right? Like, oh, this should be rejected, or this should be accepted, or this is the best paper ever read. And then there's another question generally that says, how confident are you about your evaluation? And you would think that people are like, yeah, you know what? I know that area, but I'm not the expert on that area. So no, people are like, yeah, I'm very confident. And then once in a while you see, I have been obviously area chair, program chair, and editor of many conferences and journals. And you see this, that you have sent this paper to the best person there is to review that paper. And it'll come back with, well, I'm not 100% confident, right? I mean, I could be wrong. Like, okay, we got it all backwards. And then you'll send it to someone who doesn't know much about that area. Will say, yeah, very confident. So we tend to be really bad at estimating our confidence. So there has to be some other mechanism to solve this problem. Yeah. No, because this is between 0 and 1. So you're just weighting the value that people are giving you by your confidence. Now, could you compute another statistic? Absolutely. There are many equations, criteria that have been proposed over the years to do so. So the question that you're asking is the incorrect one, right? The correct question is, under which assumptions is this model or this criterion going to work compared to any other criterion that you can come up with, right? So if you say, my data is assumed to be drawn from that specific distribution, and I can prove formally, meaning mathematically, that that will converge to the correct solution under these conditions, then those are the assumptions under which that criterion should be used, and that's what's usually done. Make sense? Okay. So last year, there was a paper in Nature that proposed a different approach, surprisingly different, but surprisingly effective approach. So let's see this. It's called the surprising popular principle. So the idea is you ask the question that you want to ask. Let's call this question 1. And then the question 2 is not how confident you are about your answer, but rather, what do you think the most popular answer will be? Okay? So it's a popularity question, popularity contest. Now, let's see an example to clarify. So again, this is the second question is what you think other people will say, right? So let's simplify this into a yes/no problem, so it seems easier, right? So without consulting your neighbors, just think about this. We don't have to write it this time. Think about answering that question. It's a yes/no question, so the answer can only be yes or no, okay? All right. Is Philadelphia the state capital of Pennsylvania? Yes or no? Think about it. All right. Mark this as yes. Don't talk to each other. Just your own feeling. Now, think about my second question then is, what do you think the most popular answer will be? Yes or no? Okay. Now, show of hands, who says yes to the first question? Is Philadelphia the state capital of Pennsylvania? Who thinks yes? Don't be embarrassed. It doesn't matter. It's fine. So I assume all the other ones say no? How about no? Who says it's not then? How about all the other people that didn't vote? It's a yes-no question. There are no third answers. Okay. So it turns out that when you ask people this is pretty much what you get. Let's see if I can find one that works. Okay. So I'm going to plot here the responses for the yes and the no. Okay. So the yes, most people generally, if you ask this, they have done experiments online to ask many people, and the majority of people say yes. So you'll get probably about this much of people that say yes, right? This much percentage. And the amount of people that say yes is probably something like this. Okay? This is the response that you see to question 1, is Philadelphia the state capital of Pennsylvania? Okay? Now, the responses to the second question go like this. This question 2. This is horrible. All right. The responses to the second question goes like this. People that answer yes, Philadelphia is of course the state capital of Pennsylvania. It's the largest city. It's the most famous city. It's where this country's constitution was established. How is it not the state capital, right? So all the people that say yes here also say yes here, okay? Or almost everyone, let's say 99.9%. Right? Now the people that answer no most likely answer no because they know that Philadelphia is not the state capital of Pennsylvania. And because they do know, they answer no. But because they know that most people are not going to know what the state capital of Pennsylvania is, they're going to answer yes here. And maybe a few of them will say, no, everyone knows that, right? I'm from Pennsylvania, everyone knows that. Right? Okay. So, here's what happens. Here's how this algorithm works. The algorithm selects the answer that's more popular than people predicted. Okay? So I'm going to select from question 1 the answer that has more votes than what people predicted that answer was going to get. Right? Did the yes vote get more votes than what people predicted they're going to get? This is actually larger, right? Because it doesn't have this section, right? So people predicted actually more than we actually got. But did the no get more votes than were actually predicted? Yes, all these votes here, right? So the no is the correct answer because it has more votes than are actually predicted. Okay, let's see the opposite case. Let me ask you another question. Is Ottawa the capital of Canada? Think about it for a second. Ottawa, the capital of Canada. Yes or no? And now, second question again. Think what other people are going to say. Yes or no? And this is what you observe when you ask people. To question 1, now most people actually know that Ottawa is the capital, so most people say yes, but surprisingly, a lot of people don't know that, so there are a lot of votes for no as well. That's pretty much what you usually get, okay? Distribution like this for the yes and the no votes. Now, what do people estimate? Well, again, here, the people that vote yes, I know Ottawa is the state, I just could state, the capital of Canada, right? Will actually know that some people, a significant number of people, don't actually know that. Some people will think it's probably Toronto or Montreal or Vancouver, right? So there are actually surprisingly going to be less yes votes here. And the people that say no will continue to say no, plus this portion of people here, so there are going to be more votes here. And what is the answer that has that is larger in question 1 than it is predicted in question 2? The yes. And therefore, yes is the correct answer. You see how this works? So you always select the answer to question 1 that has more votes than are predicted in question 2. Very simple idea, but they showed in the paper, surprisingly, when you apply this to questions like this, to questions that people have basically no idea, like estimating the cost of modern art. You know, you'll see a canvas with maybe splashes of paint. You have to estimate how much that's worth, like $10 million or $10. How would we know? It could be either, honestly, right? So it turns out that with this method, people are very good at estimating what things are worth, because you are good at estimating what others will say, right, rather than what you are saying, right? And in that case, note, you do not have to know how confident you are about the answer, because there are only two things that could happen with confidence. Either you don't know the answer, and therefore you have no idea how confident you are unless you write a 0, and then, you know, basically we don't get data. Or you just overestimate your confidence, which is typically the case. And people that do know tend to actually underestimate the confidence, right? But if you have to estimate what others will do, that's easier. And actually this method works really well. So these are techniques that you can use. We will come back to that over and over again during the course, because they are extremely useful to use in machine learning and pattern recognition to extend on the methods that we have. Yes, question? They do have a proof in the paper under certain conditions, right? So if the data is distributed according to certain specific distributions and some other conditions hold, then they can prove that that method converges to the true answer. But you have to take these proofs with a grain of salt, because are the answers really distributed according to that distribution? Most likely not, right? Are those conditions, or do these conditions occur in the world? Probably not. So they're useful, these proofs, because at least they show, well, under some conditions, that method does converge to the right answer. But at the end of the day, you just have to run a lot of experiments to see whether it works or not. Okay, any other questions? All right, so moving on, let's talk again, or let's go back to where we were with regard to our feature space. So remember, we have defined features that we extract to define our problem. We extract these features from our problem domain. With those features, we define our feature space. And now that we have a feature space, we want to start building machine learning algorithms that will give us answers to the questions that we have. All right. We've seen one very simplistic algorithm, obviously, or a set of simplistic algorithms, which is you take your sample data and you compute the mean or the median or the weighted mean or this latest method of the popularity contest and so on, right? So any statistic that you want to compute from the data is useful. But the question then becomes which ones are going to be most useful to us. And remember, going back to lecture 1, that machine learning is nothing else than y, the variable y, equals f of x, right? Where y is the output and x is the input, right? So x is known, y is not known, and I want to know what y is for a corresponding x, right? So we want to get this underlying function, right? We want to understand what that underlying function is. And that's where the learning part, as I said, of machine learning comes in. We want to learn that function. So let's just start with the problem that we discussed on Tuesday. So remember that in face recognition, we had this particular problem where we are given a set of images of faces, right? N faces. Here's the first one. Here's the second one. Right? And so on. And we call them x1, xn. Remember that the way we do that, we take x1 to be a vector of all the pixels that we have read from the very top left corner in a raster scan way. First, the first row, so it would be x11 would correspond to the first pixel of the first image. x12 would be the second pixel, the one to the right of x11, and so on until we reach the very last element of the last row, which would be, I don't know, x column row, so CR, right? And we said that we assume then that if CR equals P, then we have P pixels, right? So P, the number of pixels, that this is defined in a space of P dimensions. So P is the number of pixels. Okay, so we identified a problem with this definition of the face recognition problem already on Tuesday, which was that these values, right, these xij's here, are not really real numbers, are they? They're not. They are numbers from 0 to 255. They're integers, and therefore, really, this is a discrete feature. However, we said we want to work with random vectors, and the way to do that is to assume that these numbers are in the real domain, and that they can take any number, right, in the real domain. Okay, that's not correct, but we deal with this, right? But there is surprisingly one other thing that is incorrect in that definition. Well, not incorrect, but that is that we need to understand from this definition. Anyone can see or can tell me what the problem with this definition as is right now might be? What's our P? Let's consider R2. Let's say that the images we have only have 2 pixels, right? So R2 would look like this, right? Right? True. And it is given by some basis vectors here, right? I and j, or whatever you want to call them, right? Some basis vectors, right? What's the assumption with this? So this would represent, let's say it would represent x1. Now this is a vector, x1, right? This should be bolded x1 or x1 with a arrow if you want. I can't write bold letters in the board, so just usually leave it like this, but in the slides you will see it like this. So if I take x1, that would be x11, say here, x12 here, so maybe it'll be that vector over here, right? That could be x1, right? And then maybe I have x2 right here, x3, x4, x5, and so on, right? What's going on here? Anyone? Yeah. No, it doesn't have to, right? But something is happening here, isn't it? No. So think about this. Here, if we say this is in Rp, the basis vectors of Rp are orthogonal to one another, right? Meaning they are. What's that? Someone said, I think someone actually said it. All right, let's think about this differently. These two vectors are orthogonal to one another, right? But how about the feature vectors that we have here? Now, if I have this first dimension, right? Let's call it x1 and this one x2. I know that may be confusing for now, but let's keep this notation. x1 and x2, right? Then what does it mean for a feature x1 to be correlated with x2? What does this mean? Anyone? True, that's exactly right, that when I change x1, x2 changes, but that can also happen even when they are uncorrelated. Okay, that's not incorrect, but that's not what correlation means. Correlation means that if I have the value of x1, then the value of x2 is given as a function of x1 where this function is linear. Now that we usually call linearly correlated or linear correlations, right? And we'll talk about nonlinear correlations later on in the course. But for now, we stick to linear correlations, and that's what we usually refer to correlations. So in this particular case that I draw here, note that there is a line, right here. There's a line that perfectly predicts for any value of x1, perfectly predicts its corresponding value x2. What does this mean? That means that if I'm representing an image like this with two numbers, x1 and x2, but x2 is given as a linear function of x1, why do I keep x2? It's redundant. I don't need x2. x2 doesn't give me any additional information that I already have, beyond what I already have with x1, right? Okay. So we are interested in understanding what these correlations are. Okay? This is called feature extraction. We want to find those features that cannot be generally predicted from the other ones. We want to find the main contributors to our problem. So let's consider, we'll consider 3 cases. How about that? So this is my first case here, right? Where x1 and x2 are perfectly correlated. Now I'm going to consider another case here where my sample feature vectors look something like this. Okay, uniformly distributed across my space. So given any x1 here, there's no way for me to predict x2 because pretty much everything is possible, right? These are then uncorrelated. But there is a third option, right? The third option is that they may not be perfectly correlated, but they may not be uncorrelated either. They may look something like this. So we can probably write in this case that x2 is equal to a function of x1 plus some error function. Okay? Where again, f has to be a linear function. All right, so let's make this more formal, shall we? We have our data, our samples. Let's call them x1 through xn, right? Again, n, I'm generally going to use n for the number of samples, and p for the number of pixels or dimensions or features. For simplicity, let's assume now p equal to 2. Let's start with 2. Let's make it really simple, like these examples here. So if I have this first case right here, which defines a correlation, that's given by the equation of a line, right? So basically, the first element of this xi, right? It's going to be this one here, xi1, and xi2. It's going to be this one. So in that case, xi2 is going to be equal to the equation of a line, which is obviously, let's see, b over a x1, right? Plus d over a, right? And if I write it, I can also rewrite this. Obviously, I can move this to one side, so I can rewrite this as ax1. Actually, why don't I do I1 instead, right? I1, let's see, plus b xi2 minus d equals 0, right? And that's like this one. It's nothing else than the equation of a line, right? You agree? Where a and b are the normal of that line, and d, it's the offset, right? Correct? Okay. Now, in this case, in this first case, this equation holds, right? Which means that if I have a set of equations that I can write down, I can write say a x11 plus b x12 equals d, and all the way to xn1 xn2 equals d, right? If I have this linear system of equations, I can solve it and find a, b, and d, right? Because they are correlated, and that equation exists, right? But how about here or here? There's no solution to that system of equations, right? Now, there are obviously three options, right? I assume that I have more samples than unknowns, right? So obviously, if I have less equations than unknowns, then there's an infinite number of solutions, right? That doesn't help me. So I need to have that. And the other so this is the first case. The second case is there is a solution. It's a unique solution. And then in these other cases, which is the majority of cases, even if I have enough equations, there are absolutely no solutions, right? There's no way for me to find A, B, and D such that this equation is going to be 0 for all my simple vectors. It's impossible, right? But what we're going to do, we're going to write this as an error function. Let's call it r squared, actually. And we're going to say that I have my axi1 plus bxi2 minus d. Now, I could take the absolute value of this. I don't care if it's positive or negative. I could take the absolute value, but because the absolute value is non-differentiable, I'm going to take the square, right? Therefore, that's what this square means here. And I'm just going to add over all my simple feature vectors, right? Now, what I know is that in general, this error is going to be larger than 0. It can be 0 if and only if these dimensions are correlated, right? And when they get less and less correlated, right? So let's say correlation, we're going to assign a number of 1. It's perfectly correlated. An uncorrelated number of 0. And then something between 0 and 1 is going to define how correlated they are, right? The larger the number, the more correlated. So the larger the number of the correlation value, then the smaller this will be, right? And when I have perfect correlation equal to 1, then this will be 0. But otherwise, it'll be larger than 0. Okay, so now the question is, how do we solve this problem? I want to find now an A, B, and D that minimizes that error, right? So my goal is to minimize r squared. So let's write this in the more generic form. I'm going to say a1 xi1 plus a2 xi2 plus all the way to, let's see, we said p, right? So ap xip minus d squared, right? This is the case for 2 dimensions. This is the case for p dimensions. It's a little bit more general. And let's assume, we'll assume that d is equal to 0 for now. So if d is equal to 0, that actually simplifies a little more, right? And we have this equation. Okay, good. Now remember that that's the same as writing it this form. This form and that form are the same. So if you want to, you can also write a1 xi1 plus a2 xi2 plus and so on to AP XIP equals 0, right? And then all the way to A1 XN1 plus A2 XN2 AP XNP equals 0, right? That's just the same as this. There's no difference, right? The same equation, system of equations. But I can also write them as this. I can define a matrix X whose rows are my vectors, my sample vectors x1 through xn. And I can also define a vector A. This is a vector, which has the components A1 through AP, right? Yep. And now with this is a matrix X, capital X. This is a vector A. With that, I can rewrite this equation, right here as this multiply by this, right? Which is the same as XA square. Or if you prefer, you can decompose this as A transpose X transpose X A, right? And to simplify notation, let me call this X transpose X. I'm going to call it matrix Q. It's just the multiplication of two matrices, right? Okay, so let's look at this. We want, what's our goal? We want to minimize R2, right? Now, R2, it's equal to this equation right here. So let me write it down. It's A transpose QA, right? And what's this? This is a matrix Q that is given to me. These are my sample feature vectors. This is known to me, right? So that's just given. And this is what I need to find out. Where are the values of A, right? That's my goal. I want to find A. Okay, fair enough. But what's this equation really? This equation is nothing else than how to project the distribution of that matrix Q, right, what this Q defines, onto a space, right, a one-dimensional space defined by the vector A, right? So what I need to do is to find which projection of the matrix Q gives me the smallest possible variance in A, right, or a spread, if you will, right? That's what I'm looking for. What is that? Now, note that I can do that because Q is a symmetric matrix by definition, right? Q is X transpose X, and that by definition is a symmetric matrix. And it's also, by definition, positive defined or semi-defined, which means that all the projections I can do on A are going to be positive or 0, right? Okay. Now, when are they? Okay, this is a good question for you. When is the projection of Q going to be 0 for, or in under which condition can I project Q onto an A that's going to give me a result of 0? When they are correlated, right? Only in that particular case, when they are correlated, can I find a projection, right, a line that perfectly defines my data Q, right? That's in the only case. Otherwise, that projection is going to be positive, right? It's going to be larger than 0. Okay, good. So we know that this is, as before, either larger or equal than 0. All right, there is a well-known technique that we can use to solve that problem, which is, anyone? What's that? Well, yeah, that's linear least squares, yes. It's eigenvalue decomposition, right? So let's see that. Now, remember, this is for A. I can actually go even higher dimensions if I want. So A is going to give me the dimension. This is A vector, right? That defines the norm and the offset. We'll get back to the offset in a second. We don't have it now. But the norm of the hyperplane that gives me the correlation, the best correlation. But then I may also want to find additional hyperplanes that give me the second best correlation and the third best correlation and so on. And to do that, I can extend this equation to A transpose Q A, where A is a matrix that includes all the A1s APs. Okay. And I'm going to add an arrow here to indicate this is not A1 AP here, but rather the A's that I'm looking, okay, for the A vectors here. I don't want you to be confused. So I have this equation, right, or that equation. And now I know that I can move this around, so I can move this to the other side. We know this, let me call this, okay, let me do this. Let me call this lambda, larger or equal than 0, right? So we said that this number has to be a number that's larger or equal than 0. The same is going to apply here. A transpose QA is now going to be equal to capital lambda, where capital lambda is a diagonal matrix of lambda 1 through lambda p. Okay. All right. Now you can sort these lambdas, lambda 1 through lambda p, as either lambda 1 larger or equal than lambda 2, larger or equal than all the way to lambda p, larger or equal than 0. Or you could do it the opposite, right? You could do p is the largest and 1 is the smallest. Doesn't matter. You choose 1. And the one that we want is, remember, the top one. The one that we want is the one that gives us the smallest possible lambda. That's the smallest possible error I can ever have, right? So we really want to find this one. So lambda p, which is the smallest one, is going to give me AP, which is the dimension that defines a projection of Q that gives me the smallest variance. Lambda p minus 1 is going to be the second largest variance that defines the second projection that gives me the second smallest variance, and so on, right? And that, of course, you know, you've seen this a million times, that you can rearrange this equation here as QA equals to A lambda. And that is obviously the eigenvalue decomposition equation, right? where Q is Q A. Q is the data that we have. A is a matrix whose columns are the eigenvectors of Q, and lambda is a diagonal matrix with the corresponding eigenvalues, right? Make sense? Any questions thus far? All right, we're still not done because we still have two things to address. One is D, right? We have set D to 0, which needs not be 0, unless the data is normalized. There was a point made earlier, which is a trick that sometimes is used. And we, or I rather, made a really bold assumption at some point here in these derivations about how to compute correlations. Anyone can point me to that? All right, let me give you a hint. It's a scale problem. I made an assumption about the scale. What does, oh, wait, where am I? Okay, let me define it here. I don't know whose idea was to put this big computer in front of the board, but it's not very helpful. So that A vector that was constructed with all our unknowns, right? This vector represents what in this plot? It represents the norm of the hyperplane, right? That's what I'm looking for, right? And D the offset, remember? And what property does a norm have that I can exploit? Very good. The norm of the norm, of the normal, excuse me, is equal to 1. And that's the assumption I made when I draw these equations of the eigenvalue decomposition. I assumed that A had to have norm 1, right? Because an amount of solutions for this equation is infinite. Because if I multiply A, whatever A I find, by any scalar, any random scalar, I'm still going to have the exact same result. Nothing's going to change. And the reason is because this system of equations is a homogeneous system of equations, right? Which means that on the one side we have all zeros, and therefore multiplying the left-hand side here by any scalar is not going to change the result, right? So this solution is always up to scale. Thankfully, we know what the scale has to be, 1. So we can easily address this. And in fact, we don't really care if we were to recover a norm that was 3, length 3, because that defines the same dimension of the space as the basis vector of norm 1, right? So at the end of the day, it's a win-win. All right, very good. So now let's go back to our problem. And our problem is to fitting a line to these points. And some people that have probably taken image processing with me were already saying this is linear least squares. Very good. Yes, it is. So let's see how we can do this. Okay. Oh, wait. I think it's about time, isn't it? Is it 5:10? Right? Yeah, I'm not going to get started with this then. It's this very long. All right. Remember, there is no class next week, so I'll see you a week. So, a week from Tuesday. All right. Have a great weekend.